Welcome back to another training video using the UK Electrical Simulator. In this video, we're going to wrap up the off-grid video series, at least for now, by looking at inverter chargers. We'll discuss the different types, explain how they work in the simulator, and then add a generator to the system to show how battery charging and bypass operation works. Like the other components in an off-grid system, inverter chargers come in different types and sizes. In the real world, these can be separate units. You can have an inverter that only converts DC power into AC power, and you can have a separate charger that only charges the batteries from an AC supply. To keep things simple in the simulator, we use one device that does both jobs. It can invert DC power from the battery into 230 volt AC power for the load, and it can also charge the battery when an AC supply, such as a generator, is connected to the input side. However, like all the other components, you still need to choose the correct model for your design. A 12 volt or 24 volt inverter charger will not be suitable for a 48 volt battery bank, and a 48 volt inverter charger should only be used with a 48 volt battery system. You also need to think about how much power you want from the system. If you are only running small loads such as garden lights, a gate opener, or maybe a small fridge freezer, the power demand may be fairly low. In that type of setup, a smaller inverter charger and one suitably sized battery may be enough. You could even use a 12 volt or 24 volt system for smaller installations. However, if you are planning to run a small workshop or even supply part of a home, you will need a much larger system. That may include a larger inverter charger, more solar panels, additional solar charge controllers, and several batteries connected together to provide enough stored energy and current capacity. Another useful addition to an off-grid system is a generator, or sometimes a grid supply, used as a backup charging source. This can be especially useful during the winter months when there is less sunlight and the solar panels produce less energy. In some systems, people may also use cheaper overnight electricity to charge the batteries, then use that stored energy during the day. Another option for the winter months is to add a wind turbine, because winter often brings stronger winds. We can look at wind generation in more detail in a future video, but for now we'll focus mainly on the inverter charger and generator operation. One final point before we jump into the simulator is surge power. When choosing an inverter, you must consider not only the normal running power of your appliances, but also their startup power. A good example is a fridge freezer. Once running, it may only use a few hundred watts, but when the compressor first starts, it can briefly demand 2 or 3 times more power. So a fridge freezer that runs at around 300 watts may need 600 watts or more for a short time when it starts. This brief extra demand is called surge power. If the inverter is not rated to handle the surge, it may trip or shut down, especially if several appliances start at the same time. So, when choosing an inverter charger, always check the continuous power and the surge power rating, the battery voltage, and also its charging capability. Let's jump into the simulator and put this theory to the test. On the workspace, we have a familiar setup: 6 solar panels, a solar charge controller, one 48 volt battery, an inverter charger, and a 1 kilowatt AC load. We have also added a simple 230 volt generator, which we'll use later to demonstrate charging and bypass operation. If we double-click on the inverter charger, we can choose from several different models. Each model has different battery voltage options, AC output ratings, and charging capabilities. For this example, the selected model is a 48/3000 inverter charger. The 48 tells us it is designed for a 48 volt battery system. The 3000 refers to its apparent power rating, which is 3000 volt amps, or 3000 VA. You can also see this model has a maximum charge current of 35 amps. It is very important not to confuse VA with watts. They are related, but they are not always the same thing. VA is the apparent power. Watts is the real working power used by the load. With some AC loads, especially inductive loads such as motors, pumps, compressors, and transformers, the current and voltage are not perfectly in step with each other. This is where power factor comes in. So even though this inverter charger is rated at 3000 VA, its real working power may be around 2.4 kilowatts. Depending on the power factor allowed by the model. A simple way to think of it is this: the VA rating tells us the overall electrical demand the inverter can handle, while the watt rating tells us how much useful working power it can supply to the load. So before choosing an inverter, always check both values. Let's keep the selected model as it is, then switch on the solar charge controller and the inverter charger. We'll also set the sun slider to 100%. We can see the solar charge controller is now in bulk mode and charging the battery with almost 40 amps. At the same time, the inverter charger is taking power from the battery to supply our AC load. The load is drawing roughly 20 amps from the battery side, so this is an ideal situation. We are producing more power from the solar panels than we are using through the inverter, which means the battery is still charging. However, this will not always be the case. If the sun is hidden behind clouds or the sun drops lower in the sky, the solar panels will produce less current. When the charging current drops below the current being drawn by the load, the battery will start to discharge. Once nighttime arrives, the solar charge controller becomes idle because there is no useful solar input. The inverter can still supply the AC load, but now all the energy is coming from the battery. If we have several batteries in the system, this overnight discharge may only reduce the battery bank by a small amount. But in our current example, we only have one battery. So, if the load continues running for too long, the battery may eventually reach its low cut-off point, and the inverter charger will shut down to protect the battery. The system will then remain off or idle until the battery has recharged enough to restart. That may happen the next day when the sun returns, but only if there is enough solar energy available. This is where a separate generator, or a grid supply if available, can be useful as a backup charging source. Let's switch on the generator and see what happens. We can now see the inverter charger working as expected. The generator is supplying AC power into the input side of the inverter charger. It then uses that supply to charge the battery, while also passing power through to the AC load. This is known as bypass operation. In this example, the generator is charging the battery with around 35 amps, while also supplying the load. If we switch the load off, the bypass power to the load stops, but the charger continues to charge the battery. This is one of the main advantages of using an inverter charger instead of a basic inverter. It can supply AC power from the battery when no generator is available, but when the generator is running, it can charge the battery and supply the load at the same time. To sum up the off-grid video series, we have walked through the main components that make up a simple off-grid electrical system. We looked at how solar panels generate DC power, how panels can be connected in series, parallel, and series parallel arrangements, and how the solar charge controller manages the charging process between the panels and the battery. We looked at battery charging stages, including bulk, absorption, and float, and we compared different battery types such as lead acid, lithium iron phosphate, and sodium ion. We also looked at how batteries can be connected in parallel to increase storage capacity and current capability, and how the inverter charger converts DC battery power into 230 volts AC power. Finally, we added a generator to show how a backup AC supply can charge the battery and feed the load when there is not enough solar energy available. This gives us a basic overview of how an off-grid system works, from generation to storage to AC output, and finally to backup charging. I hope you've enjoyed this off-grid electrical series using the UK Electrical Simulator. In future videos, we'll continue building on these ideas and look at more practical examples, faults, testing, and system behaviour. Please like, subscribe, and leave a comment below.